Okay, Assalamualaikum and very good morning to everyone. Okay, so today if we continue our topic, which is process synchronizations. Okay, in this topic, you will learn about how the cooperating process will affect or be affected by other process executing in the system. So cooperating process can be either directly share a logical address space, either the code or the data, or it can be allowed to share data only through the files or messages. So in the previous chapters, you will learn how to achieve the use of threads. Okay, you will learn about the threads and the multi-threadings, how it being the concept, and also how they is being being operate. So since they have a thread and the multi-threads which is running concurrently, so the concurrent access has a possibility on the concurrent access to shared data, which can result in data inconsistency. Okay, so therefore in this chapter, you will discuss about the various mechanisms in order to ensure the orderly executions of the cooperating process that share the logical address space so that the data consistency is maintained. Okay, so kita akan maintain, kita tengok kalau dalam proses kita akan ada proses yang that concurrent process or we call a cooperating process. Okay, some threads and we have a multi-threads, okay, that running concurrently. So how they share the data, how they share the codes, okay, at the same time, they can run at the same time the data that can be accessed both process and that access concurrently can be maintained the consistency rate. So this is the object, the outline of this topic. Okay. Some of the solutions are in the hardware solution and some of them are in the software solutions. So we have to look the concept saja, yang topik subjek ni dia lebih kepada konsep. It's very important when you have a multiprocessor. So kita akan tengok kalau kita single processor, they are able to do the threads and the multi-threadings. So macam mana dia maintain dia punya data consistency dia, and then dalam masa yang sama kita akan tengok ada juga some of this concept is being used, okay, in the multiprocessing. So this is the objectives, okay, where you will be able to describe the critical section problems and illustrate the race conditions, okay, and you can see that the different solutions for the hardware solutions or the software solutions in order to maintain the synchronizations of the data or the process synchronization. So they demonstrate how the mutex logs, semaphores, monitors, and the condition variables can be used in order to solve the critical section problems, okay, and evaluate the tools that solve the critical section problems either in the low, moderate, and high contention scenarios. Okay. Okay, so previously we already discussed about the process can execute concurrently or in parallel. Okay, so kita dah tahu dah processes able dalam operating system, the process is able to can execute concurrently and it can be worked in the parallel. So this means one process may only partially complete execution before another process is being scheduled. In fact, kalau ada process, it can be interrupted before another process is being scheduled. Okay, in fact, okay, a process may be interrupted at any point in its instruction stream, and the processing core may be assigned to execute instruction of another process. Okay, additionally, okay, we already introduced to you to execute instruction of another process. Introduce a parallel executions in which two instruction streams, okay, execute simultaneously on the separate processing core. So dalam chapter ni kita akan explain macam mana concurrent ataupun parallel execution can contribute in issues that involve in the integrity of data shared by the several process. So guys, sini kita akan nampak ada beberapa isu yang perlu diberi perhatian, okay, of the programmer, especially the designers for the operating system when you run a process that running in the concurrently. So there are several issues that need to be considered. Okay. Alright. So in these issues, okay, kita akan discuss about dia punya, okay, kita akan discuss dia punya isu dia ialah, okay, kita akan tengok we have a different process, okay. For example, we have a process 0, okay, and process 1 creating the child process using the fork function ataupun kita panggil the fork system call. So namanya P0 dengan P1 ni dia ada dia punya child process, maksudnya dia ada sub process that running. So apa yang berlaku ialah, okay, apa yang berlaku ialah the race conditions akan berlaku, okay, on the kernel variables, okay, di mana dia akan represent the next available process identifier. Okay, kita tahu setiap proses ada proses identifier dia sendiri. So kalau kita ada child, fork child, maknanya dia ada sub process. So dia akan create another sub process of ID, sub process ID yang sama, tapi dia akan tahu this is belong to the fork child. Child dia 2615. Okay, so P1 dia ada dia punya ni. Okay, ataupun dia sharing the same fork child. So apa yang berlaku ialah apabila dia P0 dan P1 dia running secara concurrently dan dia akan mengakses benda yang sama, maka dia akan berlaku we call as a race condition. Okay. Alright. So in the race conditions, okay, the race condition is happens where the situation where the several process access and manipulate the same data concurrently, and the outcome of the execution depends on the particular order in which the access takes place. So dia akan ada berlaku race conditions, okay, berlaku perebutan, okay, berlumba-lumba. Dia nakkan accessing the data ataupun the resources. Contohnya dia nakkan input device ataupun dia nak output device, okay, the same forks, correct function yang tadi tu dia perlukan access pada proses pada certain data. Apabila berlaku perebutan di sini, dia akan dapati data yang diterima oleh kedua-dua tu adalah data yang inconsistent, data yang tidak boleh dipakai lah. Kalau kita dalam technical dia panggil sebagai garbage data. So dia kata as a garbage data lah. Okay. So to guard against the race condition, kita kena ensure that only one process at a time can be manipulating the variables. Okay. Kita kena pastikan dalam operating system kena pastikan benda ni. Apabila berlaku race conditions, kita make sure that only process dalam satu masa yang akan do some manipulations, okay, can access the data, and then to make sure they guarantee the process must be synchronized in the some way. Okay, right. So therefore, the situation such as the just as described tadi akan frequently operate as a different parts of the system manipulate resources. Ini selalu berlaku, bukan sahaja data, dia akan berlaku race condition dari segi resources. Okay, contohnya dua sistem nak access, dua proses nak access memori pada masa yang sama. So macam mana operating system may decide which process need to be accessed that particular memory dalam pada masa tersebut. So ini akan berlaku apabila dia berlaku cooperating ataupun berlaku dalam concurrently ataupun parallel. Kalau dia berlaku in the sequential, dia tak akan berlaku lah. Dia tak akan berlaku race condition. Okay, so furthermore dalam chapter ni kita akan tengok the growing the importance of multi-core system has brought an increased emphasis on developing multi-threaded application. So dalam ni kita akan tengok bukan sahaja single processor, kita akan tengok juga di dalam a multi-core. Multi-core maknanya you have more than one processes, okay, that running. Dan macam mana dia akan create, okay, macam mana dia boleh develop atau create the multi-threaded application. In such application, several threads which are quite possibly sharing data can be running in parallel on the different processing core. Okay, it's been clearly that we want to change the result from the such activity not to interfere with another process. Okay, kalau kita buat proses, kalau buat changes the result tu, kita nak pastikan kita nak kena pastikan aktiviti tu tak ada mengganggu atau mengganggu gugat proses yang lain. So that's why because of this importance of this issue, we devote have a major portions to have a chapter on the process synchronization and coordination among cooperating process. That's why topik ni antara topik penting dalam principle of operating system, di mana how your process can be synchronized. Okay, how your process can be synchronized. Okay, when you have a multiple process running in a multiprocessor. Alright, so each process, okay, so we have a call. Dalam ni, okay, kita akan tengok issue dulu and how we solve it. Okay, so the first thing, we begin the consideration of process synchronization by discussing the so-called critical section problems. Okay, dalam critical section problems ni, okay, we consider a system consisting of n process. Okay, kita assume saja, okay, dalam satu operating system kita ada n process. Kita tak tahu berapa banyak. Okay, dia bergantung kepada user. Okay, how many process, bergantung pada komputer, dan juga dia bergantung kepada user itu sendiri, berapa banyak program dia buka dalam masa yang sama. Then each process has a segment code, or we call as a critical section. Setiap proses ni, okay, kita consider dia ada n proses. So setiap proses dia ada critical section dia. Okay, critical section ni macam the segment of code lah. Okay, so in which process ni may be changing. Okay, bila dia ada segment of code ni, dia akan menyebabkan ada perubahan pada variable dia. Kita update the table, writing the file and so on. Banyak. Setiap section, critical section ni dia ada activity dia. Okay, antaranya ialah activity dia ialah changes dia punya variable, you update dia punya table, okay, writing the file and then banyak lagi. Okay, kalau macam you access your system tu dengan database, so you akan write the file tu akan write into database, save dalam database, lepas tu ataupun you nak buka file daripada database. Okay, so the important features of the system is that when the one process is executing in the critical sections, there's no other process is allowed to execute in its critical section. So dalam kes ini, apa yang kita buat ialah kita kena pastikan, okay, mana-mana proses yang tengah run dia punya critical section, so proses lain tidak dibenarkan, okay, dia tak benarkan execute dia punya critical section. Okay, there is no two processes, okay, are executing in their protocol that the processes can use to cooperate. So each process must request permission to enter its critical section. So untuk mengingatkan ini, apa kita buat? Setiap proses yang nakkan buat critical section, dia kena minta permission. Okay, permission in order to enter, masuk ke dalam entry critical section tadi. Okay, so bila dia minta critical sections, so how kita implement dia, kita akan letak satu section of code, implement this by request the entry section, macam function lah, kita letak satu entry function, lepas tu followed by critical section with the exit section and also the reminder section. So dia ada 3 benda. So dalam setiap proses yang masuk critical section tu, okay, dia ada 3 benda. So dia kena ada entry section, okay, lepas tu dia ada exit section, okay, and then dia ada reminder section. So critical section problem ni kita dah didesignkan as a protocol protocol rules, okay, di mana processes yang cooperate processes, okay, must follow this critical section problems. Okay, dia akan mesti, maknanya kalau setiap proses, satu proses dah masuk critical section, another proses tak boleh run or execute dia punya critical section. So setiap proses nak buat critical section kena ada permission. Okay, so bila dia ada permission, dia kena ada entry section, kena ada exit section, and also dia kena ada reminder section. So the general structure of the typical process, okay, dia akan tunjuk lah. Okay, you boleh tengok dalam buku. Okay, so the entry section and the exit section are enclosed in the boxes to highlight the importance of the segment. So kat sini. So this is general structure of the process. So they must do. So this is entry sections, okay, and you have a critical section, and then you have exit section and the reminder section. So ini dia punya algorithm lah. Okay. Right. So apa yang apa yang diperlukan for solution to critical section problem ni ada 3 benda. Okay, pertama adalah dari segi mutual exclusion. Okay, mutual exclusion adalah di mana if process is executing, any process is executing in its critical section, there's no other process can be executing in their critical section. Kalau dia tengok ada proses yang tengah run dia punya critical section, so proses lain yang nak run juga critical section kena tunggu. Okay, alright. So the progress, okay, if no process is executing in its critical section and there exist some processes that wish to enter the critical section, then the selection of the process that will enter the critical section next cannot be postponed indefinitely. So dalam syarat yang kedua dalam critical section problem, we have a progress. So progress ni dia punya syarat dia ialah kalau tak ada proses yang execute dia punya critical section dan some process dia dah request, okay, dia nak request to enter dia punya critical section, only those process that not executed in the reminder section can participate in decide which process will enter its critical section next. And this selection cannot be postponed indefinitely. Dah tak boleh postpone dah. So progress, okay. So bila tak ada proses yang executed critical section, okay, and ada some proses-proses yang sedang yang nakkan masuk critical section ni, okay, so apa yang OS akan buat selection ialah proses mana yang dia akan membuat pemilihan proses mana yang akan masuk ke dalam critical section dah tak boleh postpone dah. So dia tak ada postpone dah. Dia tak ada postpone dah. Dia terus progress masuk Okay. Dan yang ketiga ialah bounded waiting. So bounded waiting is the bound, okay, that must exist on the number of times that the other process. Okay, bounded waiting, there exists a bound or limit, okay, on the number of items that process are allowed to enter their critical section after a process has made a request to enter its critical section and before that request is made granted. So the bounded waiting ni must be exist, bound ataupun limit. The bound tu macam limit lah. Kita akan limit berapa banyak number of items, number of times of the process can be allowed to enter the critical section after a process has. Dia akan kira selepas proses tu dah request for the critical, dia dah masuk ke dalam request for to enter the critical section dan before the process can be granted dia punya requests. Okay, kita assume each process ni they execute non-zero speed. However, we can make no assumption concerning, okay, the relative speed of the end processes. Okay, at a given point in time, the many kernel mode process may be active in the operating system. So as a result, the code implementing an operating system kernel is subject to several possible race conditions. So akan berlaku. Okay, so kita continue this lecture with the interrupt-based solutions. So previously kita tahu interrupt memang dah ada dalam operating system, and operating system is a part of interrupt driver. So apa yang berlaku dalam interrupt-based solution ni ialah isu yang proses tadi ialah bila proses masuk the critical entry sections, kita dah tahu dia gunakan mutual exclusion punya syarat kan. So bila menggunakan mutual exclusion, bila proses dah masuk critical section, dah entry dah masuk entry sections, dia punya interrupt will be disabled sebab only one process can execute dia punya critical section. So proses lain tak boleh masuk, tak boleh enter the critical section. So bila dah dia exit, proses tu dah buat critical section semua, bila dia dah masuk sampai exit end section, baru interrupts will be enabled. So adakah itu akan solve the problem? Actually no, because apa yang berlaku ialah ia akan apabila ialah dia punya critical section tu, code tu run for an hours, more than 1 hours. Ni biasanya ia berlaku apabila you have a poor designs of your coding lah. So if the critical sections, code ni run for more than 1 hours. Ni proses lain tengah queue ni, proses lain pun nak run dia punya critical section problems. So critical section, so apa yang berlaku ialah bila certain proses tu, bila pakai interrupt base ni, bila critical section satu proses tu dah enter the critical sections, interrupt automatic disable. Hanya dia akan enable balik bila proses tu dah habis. The critical section dah masuk exit section, baru interrupt. Proses lain boleh interrupt dan boleh ni. Tapi kita bayangkan satu proses tu, kalau dia punya critical section tu run more than hours, more than 1 hours, several hours. So apa yang berlaku ialah it's not solve the problems. Dia akan menyebabkan berlaku proses starvation. Ataupun we call a process starve, kelaparan. So because dia tak boleh enter dia punya critical, tak boleh execute dia punya critical sections. Dan apa yang juga yang berlaku sebabkan ini, sekarang ni kita punya teknologi CPU walaupun dia single processor, tapi dia boleh have illogically, physically one processor, tapi logically kadang-kadang they have two more CPUs. So what happens? So you have not fully utilized you punya CPU. That's the problems. Some process will starve, to enter the critical section, tapi dia tak boleh masuk sebab syarat, kita ikut syarat yang pertama tadi adalah menggunakan critical section, yang mana kalau dah berlaku critical section, proses lain tak boleh execute dia punya critical section. Tapi untuk one particular processor, how about we have more than 2 processors? We have a 2 CPUs running. We have 2 CPUs. So that the issue are coming in. So low CPU utilization, low CPU utilization banyak menyebabkan proses starve, proses starving, bila you pakai interrupt based solution. Bukan kata interrupt ni tak boleh pakai, boleh. Cumanya dia akan create beberapa isu lah. Antaranya isu sebab setiap proses bila masuk entry section, disable dia akan interrupt. Dan hanya boleh dia interrupt, proses lain boleh interrupt hanya bila proses tu dah left the critical section tadi. So nak kena tunggulah. So berapa lama nak tunggu tu? Dan itu satu isu dia yang kena solve. Alright. So how we do a solution? So solution pertama ialah menggunakan software solution. Alright. So two process solutions ialah dia menggunakan solution pertama adalah dia guna process solution, iaitu assume we have a load and store machine language instruction which is atomic. atomic tu one, satu. Okay, and cannot be interrupted. So the two process share one variable. Okay, contohnya INTG turn tu. Okay, the variable turn will indicate whose turn it is to enter the critical section. So solution pertama dia ialah dia solve dengan menggunakan software solution, iaitu gunakan load and store. Load and store ni kita you dah belajar masa you dah belajar load and store ni dalam machine language. Dalam machine language kita ada satu function which is load and store, which is specific instructions, okay, that cannot be interrupt. So kalau ada load and store ni, so processor dah tahu dah, okay, kita tak boleh interrupt. Okay, so and these two machine function ni kita akan share gunakan satu variable dipanggil turn. Turn ni akan memberitahu or indicate kita siapa the next process yang akan take or enter to the critical section. Okay, so this is the punya algorithm lah. Okay, right. Okay, so okay, so kita kena correctness of the software solution. The mutual, okay, exclusion is preserved. Okay, so maknanya syarat yang pertama tadi mutual exclusion, there's no process only one. Kalau ada proses yang enter for critical section, proses lain tak boleh execute dia punya critical section. Okay, so kita dah preserve dah mutual exclusion yang pertama, di mana kita pastikan bila mana proses yang enter critical section dia akan turn, okay, the next process. Okay, so macam mana buat the progress requirement? Progress requirement tadi, kalau tak ada proses yang exist dekat dalam critical section, so dia boleh masuk kan. Dan macam mana pula dengan bounded waiting requirement tadi? Dia tak solve lagi. So maknanya interrupt based solution yang kita bagi tadi, dia hanya boleh solve the mutual exclusion saja, tapi dia tak solve the progress requirement dan juga bounded waiting punya syarat. Okay, so that's why we come up with the one solution, okay, which is the Peterson's solution. So Peterson's solution ni, they use two process solution. This is a classic software based solution to the critical section that dia panggil sebagai Peterson's solution. Okay, so because of the way of modern computer architecture perform the basic machine language such as load and store, then there's no guarantee that Peterson's solution ni will work correctly on the modern punya computer architecture. Okay, macam modern computer architecture contohnya pakai object oriented, okay, multi-threading, so it's not guaranteed. So however, we present the solution because they provide a good algorithmic descriptions of how to solving the critical section problem and illustrate some of the complexity involved in designing software that address the requirement of mutual exclusion, progress and the bounded waiting. So walaupun Peterson's solutions ni is a classic software solution, okay, tapi tak menjamin ianya boleh digunakan dalam modern computer architecture. Tapi oleh kerana kenapa kita discuss juga this kind of solutions, kerana dia provide a good descriptions dari segi algorithm dia dalam nak solve critical section problem lah. Okay, di mana dia boleh address bila dia design the software Peterson's solution ni, dia boleh address requirement untuk mutual exclusion, the progress dan juga the bounded waiting. Okay, so dalam Peterson's solution ni, dia suggest two process solution. And then we have the load and store machine language, which will be instruction that will be atomic and that cannot be interrupted. So the two process share the two variables, okay, which is int turn dan juga boolean flag. So variable turn ni akan indicate proses yang mana yang akan the next process yang akan enter the critical section, and the flag array ni akan indicate which process is ready to enter the critical section. So dia apply lah, okay, so apply the mutual exclusion. So dia take turn, okay, untuk proses next proses yang akan enter the critical section, dan dia akan bagi tahu array indicate proses mana yang akan ready untuk enter the critical section. So this is the so Peterson restricted to process the alternate execution between the critical section and the remainder section. So the process are numbered, okay, for example P0 and P1, okay. So for convenience, we're representing Pi, we use Pj to denote another process that use J equals to 1 minus I. So Peter's solutions provide two process that to share data item, iaitu empty turn dan juga boolean flag. So dalam the variable turn ni, macam kita cakap tadi, indicate whose turn to be entered the critical section. Okay, then the process, okay, if the turn equals to I, then the process akan allowed to execute the critical section. So the flag array tadi akan used to indicate the process that is to be ready to enter its critical section. So kalau the flag to true, so this value will indicate the Pi is ready to enter the critical section. Okay. Okay, to enter the critical section, process ni akan set as a flag I to be true and then set turn to be value J. So kita nak bezakan so there why they assert that if the other process wish to enter the critical section, it can do so. If both process try to enter at the same time, the turn will be set to both I and J roughly at the same time. Okay, dia guna N kan. So only one of these assignment will last, okay, and the order will be occur but will be overwritten immediately. So the eventual value of turn determines which of the two process is allowed to enter its critical section first. So now kita boleh buktikan, okay, we can prove that this solution is correct. Okay, di mana so Peterson solutions ni provide the three requirement. Okay, critical section requirement. Met the critical section punya requirement lah. First, the mutual exclusion is preserved. Okay, di mana the process enter CS only if they false or turn into I. Okay. And the progress requirement is satisfied, and the bounded waiting requirement also is met. Okay. Okay. So although useful, okay, walaupun Peterson solutions ni, okay, can demonstrate, okay, a good algorithms, okay, but it cannot guarantee to work in the modern architecture with the current architecture, because they have to improve the performance, the processes, or the compiler may be reorder operations that have no dependency. So understanding why it works not work is useful for better understanding the race conditions. Okay, for single threaded this is okay, as the result will always be the same. So dalam Peter solutions ni, okay, untuk classic punya boleh, okay, classic punya architecture boleh, okay. For single threads it can be happens, okay, it's okay. For alright, we have good result, but with the current, okay, modern architecture such as a multi-threading, okay, we have a multiprocessing, symmetric multiprocessing, lepas tu kita ada asymmetric multiprocessing, okay, so it not produce inconsistent or unexpected results, okay. So that's why the Peterson solutions ni only can classify as a classic software solutions.